Right now, as you watch this video, you are traveling through space at 515,000 miles per hour. Not because Earth is orbiting the Sun, not because our solar system is moving through space, but because our entire galaxy, the Milky Way, is rotating like a massive cosmic pinwheel, carrying our solar system and hundreds of billions of other stars in a grand celestial dance that takes 225 million years to complete one full rotation. To put this mind-bending speed in perspective, you could travel from Earth to the Moon in just 28 minutes at the Milky Way's rotational velocity. For most of human history, we had no idea we were passengers on this galactic merry-go-round. We thought the stars were fixed points of light in an unchanging celestial sphere, that the universe was static and eternal. We were completely wrong. The Milky Way is a dynamic, evolving structure where every star, every planet, every speck of cosmic dust is participating in a gravitational ballet of staggering complexity and beauty. Tonight, we re-embarking on a journey through space and time to understand one of the most fundamental motions in the cosmos. You will discover exactly how astronomers measured the Milky Way's rotation despite being embedded within the galaxy itself. Learn about the invisible forces that drive this cosmic motion, and explore what our galaxy's rotation reveals about the structure and evolution of the universe. Chapter 1. Motion Discovery. The revelation that our entire galaxy rotates at 515,000 miles per hour represents one of the most profound discoveries in the history of astronomy, fundamentally changing our understanding of cosmic structure and our place within it. This discovery required decades of careful observations, mathematical analysis, and technological innovation to measure motions across distances so vast that light itself takes thousands of years to cross them. Understanding how we discovered galactic rotation reveals both the ingenuity of astronomical detective work and the shocking moment when humanity realized we live inside a spinning cosmic structure of unimaginable scale. The story begins in the early 20th century with Harlow Shapley's groundbreaking work at Harvard College Observatory. Shapley was studying globular clusters, dense collections of ancient stars that orbit around the Milky Way like satellites. By measuring the distances to these clusters using variable stars as cosmic lighthouses, Shapley made a startling discovery. The globular clusters were not uniformly distributed around the sky as expected, but were strongly concentrated toward the constellation Sagittarius. This asymmetric distribution led Shapley to a revolutionary conclusion. Our solar system was not located at the center of the galaxy as astronomers had assumed, but rather in the outer regions, approximately 26,000 light-years from the galactic center. This discovery immediately raised a crucial question. If we relocated in the galactic suburbs rather than downtown, how does our cosmic neighborhood maintain its position relative to the galactic center? Dr. Harlow Shapley's realization of our eccentric position led him to propose that the entire galaxy must be in motion, with different regions orbiting around the central mass concentration. But proving this hypothesis required measuring the actual velocities of stars across the galaxy, a task that seemed impossible given the enormous distances and tiny angular motions involved. The breakthrough came through the application of spectroscopy, the technique of analyzing light to determine the motion of celestial objects. When stars move toward or away from us, their light undergoes a Doppler shift, the same effect that makes an ambulance siren change pitch as it passes by. By measuring these Doppler shifts in stellar spectra, astronomers could determine the radial velocities of stars throughout the galaxy with extraordinary precision. Jan Oort, a Dutch astronomer working in the 1920s, became the first person to successfully measure galactic rotation by analyzing the motions of thousands of stars in our cosmic neighborhood. Oort's analysis revealed that stars closer to the galactic center orbit faster than stars farther out, exactly as predicted by Kepler's laws of orbital mechanics. This differential rotation provided the first direct evidence that our galaxy behaves like a gravitationally bound system rather than a random collection of stars. Oort's calculations showed that stars in our region of the galaxy, about 26,000 light-years from the center, orbit at approximately 220 kilometers per second, or roughly 492,000 miles per hour. The mathematical framework for understanding galactic rotation draws directly from celestial mechanics principles established by Johannes Kepler and Isaac Newton. Just as planets orbit the Sun according to well-defined laws that relate orbital speed to distance from the central mass, stars orbit the galactic center following similar principles, but operating on scales millions of times larger and involving gravitational fields generated by hundreds of billions of stars. However, early measurements of galactic rotation immediately revealed a puzzling discrepancy. According to Kepler's laws, orbital velocity should decrease with distance from the central mass, just as outer planets orbit the Sun more slowly than inner planets. But observations showed that stellar velocities remained roughly constant across large regions of the galaxy, creating what astronomers call a flat rotation curve. This flat rotation curve posed a fundamental challenge to our understanding of galactic structure. If most of the galaxy's mass were concentrated in the central regions, as visible light observations suggested, then our stars should be moving much more slowly than observed. The fact that they maintain high orbital velocities implied that either our understanding of gravity was wrong, or the galaxy contained much more mass than we could see. Dr. Vera Rubin's systematic study of galactic rotation in the 1970s provided the definitive evidence for this mass discrepancy. Using the new technology of image tube spectrographs, Rubin and her colleague Kent Ford measured the rotation curves of dozens of galaxies with unprecedented precision. Their work confirmed that the flat rotation curve phenomenon was universal among spiral galaxies, not just a peculiarity of the Milky Way. Rubin's discovery led to the revolutionary conclusion that galaxies must be embedded within massive halos of invisible dark matter, material that interacts gravitationally but doesn't emit or absorb light. This dark matter apparently outweighs visible matter by a factor of 5 to 1 throughout the universe, making it the dominant component of galactic mass and the primary driver of galactic rotation. The measurement techniques that reveal galactic rotation continue to evolve with advancing technology. The Hipparcos satellite, launched in 1989, provided precise measurements of stellar positions and motions for over 100,000 stars, while the more recent Gaia mission has extended these measurements to over 1 billion stars throughout the galaxy. These space-based observations have confirmed the basic picture of galactic rotation while revealing additional complexities in stellar motions. Modern radio astronomy has revolutionized our ability to map galactic rotation by observing the 21-centimeter hydrogen line, radio waves emitted by neutral hydrogen gas throughout the galaxy. Unlike visible light, radio waves can penetrate the dust clouds that obscure much of the galactic disk, allowing astronomers to map rotation patterns across the entire Milky Way rather than just our local neighborhood. The discovery of galactic rotation also revealed the timescales involved in cosmic evolution. At our solar system's orbital velocity of 515,000 miles per hour, it takes approximately 225 million years to complete one orbit around the galactic center. This period, known as a galactic year or cosmic year, provides a new perspective on cosmic timescales and the history of life on Earth. Since the formation of our solar system, 4.6 billion years ago, we have completed roughly 20 orbits around the galactic center. This means that during Earth's entire history, our planet has traveled a distance equivalent to orbiting a circle with a circumference of about 165,000 light-years. A journey of over 3 million light-years through space while remaining gravitationally bound to our parent galaxy. The measurement of galactic rotation has profound implications for understanding stellar formation and evolution. The gravitational forces that drive galactic rotation also compress gas clouds and trigger star formation, while the orbital motions of stars mix heavy elements throughout the galaxy and influence the chemical evolution of stellar populations. Understanding galactic rotation also provides insights into galactic collisions and mergers, which play crucial roles in cosmic evolution. When galaxies approach each other, their rotation patterns become distorted through tidal interactions, often triggering bursts of star formation and fundamentally altering galactic structure. The techniques developed to measure galactic rotation have found applications throughout astronomy, from mapping the internal structure of other galaxies to detecting exoplanets through their gravitational effects on stellar motion. The precision required to measure galactic rotation has pushed astronomical instrumentation to extraordinary levels of sensitivity and accuracy. Dr. J. Lockman from the National Radio Astronomy Observatory reflects on the significance of galactic rotation discovery. Measuring galactic rotation taught us that we live in a dynamic universe where everything is in motion on cosmic scales. This discovery connected local stellar motions to the large-scale structure of the universe and revealed that invisible matter dominates cosmic dynamics. The discovery that our galaxy rotates at 515,000 miles per hour transformed astronomy from a science that studied static celestial objects to one that investigates dynamic cosmic systems evolving over billions of years. This shift in perspective continues to drive modern astrophysics and cosmology as we seek to understand how the universe's largest structures form and evolve. The motion discovery revealed that our cosmic address is far more dynamic than anyone had imagined. We are not simply residents of a solar system orbiting a star, but passengers on a cosmic journey that carries us through galactic space at speeds that dwarf anything achievable through human technology. Participating in gravitational dynamics that operate on scales spanning hundreds of thousands of light years, and time periods measured in hundreds of millions of years. Chapter 2. Scale Revelation 2. Truly comprehend the significance of the Milky Way's 515,000 mile-per-hour rotation, we must first grasp the almost incomprehensible scale of our galaxy itself. The Milky Way isn't just large. It is so vast that human language struggles to convey its true dimensions. Understanding the galactic scale reveals why the rotation speed that carries us through space is both necessary to maintain galactic structure and representative of gravitational forces operating on scales that dwarf anything in our terrestrial experience. The Milky Way galaxy spans approximately 100,000 light-years in diameter, with our solar system located about 26,000 light-years from the galactic center. To put this in perspective, if our solar system were the size of a quarter, the Milky Way would be larger than the continental United States. Light traveling at 186,000 miles per second, the fastest possible speed in the universe, takes 100,000 years to cross from one edge of our galaxy to the other. This scale becomes even more staggering when we consider that the 515,000 mile-per-hour speed that carries our solar system around the galactic center covers a distance of approximately 165,000 light-years in one complete orbit. Each galactic year, the time it takes to complete one rotation, our solar system travels a distance equivalent to 1.5 times the diameter of our entire galaxy, yet we remain gravitationally bound within this cosmic structure throughout the journey. Dr. Robert Kirshner from Harvard University explains the scale challenge. Human brains evolved to navigate environments measured in meters and kilometers, but galactic astronomy requires us to think about distances measured in tens of thousands of light years and time periods measured in hundreds of millions of years. The Milky Way operates on scales where our normal intuition about space and time completely breaks down. The mass contained within this enormous galactic structure provides another perspective on cosmic scale. The Milky Way contains an estimated 100 to 400 billion stars, each with its own gravitational field contributing to the overall galactic dynamics. If you could count one star per second without stopping, it would take between 3,000 and 12,000 years to count every star in our galaxy, longer than all of recorded human history. But stars represent only the visible tip of the galactic iceberg. The total mass of the Milky Way, including dark matter, is estimated at roughly 1 to 2 trillion times the mass of our Sun. This enormous mass generates the gravitational field that maintains galactic rotation and keeps hundreds of billions of stellar systems bound together in an organized structure that has persisted for over 13 billion years. The thickness of the galactic disk provides another dimension of scale that affects how we understand galactic rotation. The Milky Way's stellar disk is approximately 1,000 light-years thick at our location, creating a relatively thin structure compared to its diameter. This disk-like geometry means that most of the galaxy's mass is concentrated in a relatively flat plane, which significantly influences how gravitational forces shape orbital motions. Within this vast galactic disk, the 515,000 mile-per-hour rotation creates a dynamic environment where stellar densities, gravitational fields, and orbital velocities vary dramatically depending on location. Near the galactic center, stars are packed thousands of times more densely than in our solar neighborhood, while the outer regions contain stellar densities far lower than our local environment. The scale of galactic rotation becomes even more impressive when we consider the precision required to maintain stable orbital motions across such enormous distances. The gravitational forces that keep our solar system in its galactic orbit must balance perfectly with the centrifugal forces created by our 515,000 mile-per-hour velocity. Any significant imbalance would either send us spiraling toward the galactic center or flying off into intergalactic space. This gravitational balance operates across the entire galaxy, maintaining organized rotation patterns that span scales from individual stellar systems to the galaxy's outer edge. The mathematical precision required for this cosmic choreography rivals anything found in human engineering, yet it emerges naturally from the fundamental laws of physics operating on galactic scales. The spiral arm structure of the Milky Way adds another layer of complexity to galactic scale. These enormous spiral features stretch for tens of thousands of light years and contain enhanced densities of stars, gas, and dust. Our solar system's 515,000 mile-per-hour motion carries us through different spiral arms over time periods of tens of millions of years, exposing Earth to varying levels of cosmic radiation and potentially influencing the evolution of life. The timescales associated with galactic rotation provide a fundamentally different perspective on cosmic evolution. At 515,000 miles per hour, our solar system has completed only about 20 orbits since its formation 4.6 billion years ago. This means that galactic rotation operates on timescales comparable to the entire history of life on Earth, connecting local biological evolution to cosmic dynamics. Understanding galactic scale also reveals why measuring the Milky Way's rotation required such sophisticated observational techniques. The angular motions of stars due to galactic rotation are incredibly small, typically measured in milliseconds per year. Detecting such tiny motions across galactic distances requires instrument precision that pushes the limits of current technology. The scale revelation extends beyond physical dimensions to encompass energy scales as well. The kinetic energy contained in the Milky Way's rotation is approximately joules, a number so large that it exceeds the total energy output of our Sun over its entire 10 billion year lifetime by factors of billions. This enormous energy reservoir represents one of the largest concentrations of kinetic energy in the observable universe. Comparative galactic studies have revealed that the Milky Way's scale and rotation speed place it among the larger galaxies in the universe, though far from the largest. Giant elliptical galaxies can contain trillions of stars and span hundreds of thousands of light years. While dwarf galaxies may contain only a few billion stars within regions smaller than the distance from our solar system to the galactic center, the scale of dark matter halos surrounding galaxies like the Milky Way extends far beyond the visible galactic disk. Current models suggest that our galaxy, as dark matter halo, may extend to distances exceeding 300,000 light-years from the galactic center, 3 times the diameter of the visible galaxy. This invisible mass distribution plays a crucial role in maintaining the rotation patterns we observe. Recent discoveries have revealed that galactic scale extends even beyond individual galaxies to encompass vast cosmic webs of galaxies, gas, and dark matter that span hundreds of millions of light-years. The Milky Way's motion through this cosmic web adds additional velocity components that must be considered when calculating our total cosmic speed. The scale revelation has profound implications for understanding our cosmic significance. From a galactic perspective, our entire solar system occupies a volume so small that it would be undetectable in observations of distant galaxies. Yet this tiny region contains all of known life in the universe, highlighting the extraordinary contrast between cosmic scales and the scales relevant to biological existence. Modern space missions like the Gaia satellite are revolutionizing our ability to map galactic structure and understand scale relationships throughout the Milky Way. By measuring the positions and motions of over 1 billion stars, Gaia is creating the most detailed map ever made of galactic structure and dynamics, revealing new complexities in how rotation patterns vary across different regions of the galaxy. The scale revelation also connects galactic dynamics to fundamental physics in ways that continue to challenge our understanding of gravity, dark matter, and cosmic structure formation. The fact that such enormous gravitational systems can maintain coherent rotation patterns over billions of years suggests that the universe operates according to physical principles that create remarkable stability on cosmic scales. Dr. Gary Gilmore from Cambridge University reflects on galactic scale. Understanding the true scale of the Milky Way forces us to recognize that we inhabit a cosmic structure whose size and complexity exceed human comprehension. The 515,000 mile-per-hour rotation that carries us through space operates on scales that connect the smallest details of stellar motion to the largest structures in the universe. The scale revelation transforms our perspective on cosmic motion from an abstract, astronomical concept to appreciation for the extraordinary gravitational architecture that maintains organized motion across scales spanning tens of thousands of light-years and time periods measured in hundreds of millions of years, demonstrating how the universe creates stable, long-term structures through the elegant application of fundamental physical laws. Chapter 3. Dark Matter Mystery, the driving force behind the Milky Way. This 515,000 mile-per-hour rotation represents one of the greatest unsolved mysteries in modern physics. According to our best understanding of gravity and the visible matter we can observe in our galaxy, the outer regions of the Milky Way should be rotating much more slowly than they actually are. The fact that stars maintain such high orbital speeds throughout the galactic disk can only be explained by the presence of vast amounts of invisible dark matter that outweighs visible matter by a factor of 5 to 1. This dark matter mystery emerged from careful observations of galactic rotation curves in the 1970s, when astronomer Vera Rubin and her colleagues measured the orbital velocities of stars and gas clouds throughout spiral galaxies. Classical physics predicted that these rotation curves should decline with distance from the galactic center, just as planetary velocities decrease with distance from the Sun. Instead, Rubin discovered that rotation velocities remain roughly constant across large regions of galactic disks, creating flat rotation curves that seem to violate fundamental principles of orbital mechanics. Dr. Vera Rubin's discovery revolutionized our understanding of cosmic composition. Her observations revealed that visible matter, stars, gas, and dust represents only about 15% of the total mass needed to explain galactic rotation patterns. The remaining 85% consists of dark matter that interacts gravitationally but doesn't emit, absorb, or scatter electromagnetic radiation in any detectable way. The implications of this discovery are staggering. Dark matter apparently forms massive halos that extend far beyond the visible boundaries of galaxies, creating gravitational fields that dominate galactic dynamics. In the Milky Way, this dark matter halo may extend to distances exceeding 300,000 light-years from the galactic center, containing more mass than all the visible stars, gas, and dust in our galaxy combined. Understanding how dark matter influences the Milky Way's rotation requires grasping the relationship between orbital velocity and gravitational mass. In a solar system where most mass is concentrated in the central star, orbital velocities follow Kepler's laws and decrease with distance. But in a galaxy embedded within a dark matter halo, the mass distribution is more complex, with significant amounts of mass extending to large radii. Computer simulations of dark matter halos reveal complex three-dimensional structures that help explain observed galactic rotation patterns. These simulations show that dark matter forms extended distributions with densities that decrease gradually with distance from galactic centers, creating gravitational fields that can maintain high orbital velocities throughout galactic disks. The nature of dark matter itself remains one of the deepest mysteries in physics. Despite decades of research, scientists still don't know what dark matter is made of, how it interacts with normal matter, or why it doesn't emit light. The leading theoretical candidates include exotic particles that interact only through gravity and the weak nuclear force. But direct detection of dark matter particles has so far proven elusive. Dr. Catherine Fries from the University of Michigan, who studies dark matter physics, explains the mystery. Dark matter shapes the largest structures in the universe and drives galactic rotation, yet we can't see it, touch it, or directly detect it in our laboratories. Understanding dark matter represents one of the fundamental challenges facing modern physics. The distribution of dark matter within the Milky Way affects not only galactic rotation, but also the formation and evolution of stellar systems throughout the galaxy. Dark matter's gravitational influence helps trigger star formation by compressing gas clouds, while its large-scale distribution affects how heavy elements spread throughout the galactic disk over billions of years. Recent observations have revealed that dark matter distributions vary significantly among different types of galaxies, providing clues about how dark matter halos form and evolve. Some dwarf galaxies appear to be almost entirely dominated by dark matter, while others show evidence for dark matter distributions that have been altered by stellar feedback processes. The search for dark matter has spawned numerous experimental approaches, from underground detectors designed to catch dark matter particles colliding with normal matter to space-based telescopes that map dark matter distributions through gravitational lensing effects. These experiments are gradually constraining the properties of dark matter and ruling out various theoretical candidates. Alternative theories to dark matter have been proposed to explain galactic rotation patterns, including modified theories of gravity that behave differently on galactic scales. However, most of these alternatives face challenges in explaining the full range of astronomical observations, from galactic rotation curves to the formation of large-scale cosmic structures. The cosmic microwave background radiation, the afterglow of the Big Bang, provides independent evidence for dark matter's existence and abundance. Detailed measurements of this radiation reveal patterns that can only be explained if dark matter comprises roughly 27% of the total mass energy content of the universe, compared to just 5% for normal matter. Galaxy collision simulations have provided some of the most compelling evidence for dark matter's reality. When galaxies collide, their dark matter halos pass through each other relatively unaffected, while the normal matter experiences friction and heating. This separation between dark matter and normal matter has been directly observed in colliding galaxy clusters, providing strong support for dark matter's particle nature. The role of dark matter in galactic formation and evolution extends far beyond just maintaining rotation curves. Dark matter apparently provided the gravitational scaffolding that allowed the first galaxies to form in the early universe, while its continued presence influences how galaxies merge and evolve over cosmic time. Modern surveys are mapping dark matter distributions throughout the universe using gravitational lensing techniques that can detect dark matter's gravitational effects on light from distant galaxies. These observations reveal that dark matter forms a cosmic web of filaments and nodes that spans the entire observable universe, with galaxies forming at the intersections of this dark matter network. The search for dark matter particles continues to drive innovation in experimental physics. Underground laboratories around the world house sensitive detectors designed to catch dark matter particles, while particle accelerators attempt to create dark matter in high-energy collisions. The discovery of dark matter's true nature would represent one of the most significant breakthroughs in the history of science. Theoretical physicists have proposed numerous candidates for dark matter particles, from weakly interacting massive particles, WIMPs, to axions to sterile neutrinos. Each possibility has different implications for how dark matter behaves and how it might be detected, leading to diverse experimental approaches for dark matter discovery. The influence of dark matter on stellar formation processes affects the chemical evolution of galaxies and ultimately influences the conditions necessary for planet formation and life. Understanding dark matter's role in galactic dynamics provides insights into how the universe creates environments suitable for complex chemistry and biological evolution. Recent computer simulations of galaxy formation have revealed that dark matter's properties must be fine-tuned to allow galaxy formation at all. If dark matter interacted too strongly with itself or with normal matter, galaxies would not form as we observe them. This fine-tuning adds another layer to the dark matter mystery. The discovery that dark matter drives galactic rotation has fundamentally changed our understanding of cosmic evolution and structure formation. Rather than being dominated by visible matter, as astronomers assumed for centuries, the universe is primarily composed of invisible components that we're only beginning to understand. Dr. Carlos Frank from Durham University, who studies cosmic structure formation, reflects on the dark matter mystery. Dark matter represents our ignorance about 85% of the matter in the universe. This invisible component drives galactic rotation, shapes cosmic structure, and influences the formation of planets and stars. Yet we still don't know what it's made of. The dark matter mystery surrounding the Milky Way's rotation connects local galactic dynamics to fundamental questions about the nature of matter, gravity, and cosmic evolution. Solving this mystery will require breakthroughs in both theoretical physics and experimental technology, potentially revealing new physics beyond our current understanding. Understanding dark matter's role in driving galactic rotation at 515.0 miles per hour demonstrates how the most familiar motions in our cosmic neighborhood depend on invisible forces and unknown particles that dominate the universe yet remain tantalizingly beyond our current ability to directly detect or understand. Chapter 4. Stellar traffic within the Milky Way's grand rotation at 515,000 miles per hour lies a complex symphony of individual stellar motions that create patterns resembling cosmic traffic flows on scales that span thousands of light years. Each of the galaxy's hundreds of billions of stars follows its own unique orbital path. Yet these individual motions combine to create organized structures and circulation patterns that reveal the underlying gravitational architecture governing our galactic neighborhood. Understanding stellar traffic requires recognizing that the Milky Way's rotation isn't like a solid wheel spinning uniformly. Instead, it exhibits differential rotation, where stars at different distances from the galactic center orbit at different speeds, creating complex relative motions that astronomers call stellar kinematics. These motions affect everything from the formation of spiral arms to the mixing of heavy elements throughout the galactic disk. Our solar system's motion through this stellar traffic provides a perfect example of how complex galactic kinematics can be. While we orbit the galactic center at approximately 515,000 miles per hour, we also move relative to nearby stars in our local galactic neighborhood. This motion carries us through different stellar environments over time periods of millions of years, exposing Earth to varying levels of cosmic radiation and potentially influencing biological evolution. Dr. Catherine Pilachowski from Indiana University, who studies stellar motions, explains the complexity. Stellar kinematics in the Milky Way resembles traffic in a massive city where every vehicle follows its own route, yet patterns emerge that reveal the underlying road network. Understanding these patterns helps us map galactic structure and evolution. The local standard of rest provides astronomers with a reference frame for measuring stellar motions within our galactic neighborhood. This conceptual framework represents the average motion of stars in our local region, allowing astronomers to identify stars with unusual velocities that might indicate different stellar populations or origins. High-velocity stars represent some of the most dramatic examples of stellar traffic in our galaxy. These objects move at speeds exceeding 300 kilometers per second relative to local standard of rest, fast enough to escape the galaxy entirely. Some high-velocity stars appear to have been ejected from the galactic center by gravitational interactions with the supermassive black hole, while others may be visitors from other galaxies or remnants of disrupted stellar systems. The discovery of stellar streams provides direct evidence for how galactic tidal forces affect stellar traffic patterns. These linear structures consist of stars that were once part of globular clusters or dwarf galaxies that have been tidally disrupted by the Milky Way's gravitational field. As these objects orbit through the galaxy, tidal forces stretch them into long streams that can extend for thousands of light years. Stellar age populations exhibit different kinematic properties that reflect the galaxy's dynamical evolution over billions of years. Old stars in the galactic halo display more random orbital motions, while younger stars in the galactic disk participate more directly in organized rotation patterns. These differences provide insights into how the Milky Way assembled and evolved through cosmic time. The thick disk population represents an intermediate stellar component with kinematic properties between the thin disk and halo populations. These stars exhibit higher velocity dispersions and different chemical compositions compared to thin disk stars, suggesting they formed during an earlier epoch when the galaxy experienced more violent dynamical processes. Gravitational interactions between stars can occasionally alter stellar trajectories dramatically, creating runaway stars that escape their birth environments with velocities exceeding 50 kilometers per second. These interactions are most common in dense stellar environments like star clusters, where close encounters can provide sufficient gravitational kicks to alter stellar orbits significantly. The motion of our solar system relative to nearby stars creates the phenomenon of stellar aberration, where the apparent positions of stars shift slightly due to our motion through space. This effect, combined with stellar parallax measurements, allows astronomers to determine three-dimensional stellar positions and velocities with extraordinary precision. Binary star systems add another layer of complexity to stellar traffic patterns. These gravitationally bound pairs orbit around their common center of mass while participating in galactic rotation, creating complex three-body dynamics when their orbital motions are considered alongside galactic gravitational fields. The Gaia space mission has revolutionized our understanding of stellar traffic by measuring precise positions, distances, and motions for over 1 billion stars throughout the Milky Way. These observations reveal previously unknown stellar streams, moving groups, and kinematic structures that provide new insights into galactic dynamics and evolution. Stellar moving groups represent collections of stars that share similar space velocities and ages, suggesting they form together and are traveling through the galaxy as loose associations. These groups provide natural laboratories for studying stellar evolution and the effects of galactic tidal forces on stellar clusters. The local bubble, a region of hot, low-density gas surrounding our solar system, affects stellar traffic patterns by creating different environments for stellar motion and evolution. This bubble, created by ancient supernova explosions, spans approximately 300 light-years and influences how gas, dust, and cosmic rays flow through our galactic neighborhood. Velocity ellipsoids describe the three-dimensional distribution of stellar velocities in different regions of the galaxy. These mathematical constructs reveal how stellar motions are organized by galactic gravitational fields and provide insights into the mass distribution and dynamical history of different galactic components. The phenomenon of galactic cannibalism affects stellar traffic on large scales as the Milky Way continues to accrete smaller satellite galaxies. The gravitational disruption of these systems creates streams of stars with distinctive kinematic signatures that can persist for billions of years after the original galaxies have been completely destroyed. Resonance phenomena in galactic dynamics create preferred locations where stellar orbits interact with spiral arm patterns or bar structures. These resonances can trap stars in specific orbital configurations or cause them to migrate radially through the galactic disk over extended time periods. The study of stellar traffic patterns has revealed that the Milky Way's disk is not perfectly flat but exhibits warping and flaring at large radii. These distortions affect stellar orbits and create three-dimensional traffic patterns that extend well above and below the main galactic plane. Asymmetric drift describes how stellar velocity distributions change with age and stellar population, reflecting the dynamical heating that occurs as stars interact gravitationally with molecular clouds, spiral arms, and other galactic structures over billions of years. The discovery of hypervelocity stars, objects moving at speeds exceeding 700 kilometers per second, has revealed extreme examples of stellar traffic that challenge our understanding of galactic dynamics. These stars appear to have been ejected from the galactic center by interactions with the supermassive black hole or possibly by other exotic mechanisms. Recent observations have identified co-moving stellar groups that share common motions despite being separated by hundreds of light-years. These extended associations provide evidence for large-scale coherent motions in a galactic disk and may represent the dispersed remnants of ancient star-forming regions. The metallicity gradient in the galactic disk, the tendency for outer regions to contain lower abundances of heavy elements, reflects how stellar traffic patterns mix processed material throughout the galaxy over cosmic time. Understanding this gradient provides insights into galactic chemical evolution and star formation history. Stellar traffic analysis has revealed that our solar system's orbit around the galactic center is not perfectly circular, but exhibits slight eccentricity that carries us through different galactic environments over time periods of tens of millions of years. These orbital variations may influence Earth's climate and biological evolution through changes in cosmic ray exposure. Dr. Rosemary Wise from Johns Hopkins University reflects on stellar traffic complexity. The Milky Way as stellar kinematics reveal a galaxy that's far more dynamic and structured than we once imagined. Every star follows its own unique path through space, yet these individual motions combine to create organized patterns that tell the story of galactic formation and evolution. The study of stellar traffic patterns continues to reveal new aspects of galactic dynamics and structure. Advanced statistical techniques applied to Gaia data are uncovering subtle kinematic features that provide insights into dark matter distributions, past merger events, and the detailed gravitational potential of the Milky Way. Understanding stellar traffic within our galaxy, S515. 0-mile-per-hour rotation demonstrates how individual stellar motions contribute to large-scale galactic dynamics while revealing the complex gravitational environment that shapes stellar evolution and influences the conditions for planet formation throughout the galaxy. Chapter 5. Measurement methods determining that the Milky Way rotates at 515,000 miles per hour represents one of the most challenging measurement problems in astronomy, requiring techniques that can detect tiny motions across distances spanning thousands of light years. The methods developed to measure galactic rotation have pushed observational astronomy to extraordinary levels of precision, employing everything from subtle Doppler shifts in stellar spectra to precise positional measurements of stars over decades of observation. The fundamental challenge in measuring galactic rotation stems from our location within the galaxy itself. Unlike distant galaxies that we can observe from the outside, we must determine the Milky Way's rotation from our position embedded within the galactic disk, approximately 26,000 light-years from the center. This requires disentangling our own motion from the motions of stars throughout the galaxy while accounting for complex three-dimensional velocity distributions. Spectroscopic techniques provide the foundation for most galactic rotation measurements by detecting Doppler shifts in the light emitted by stars and gas clouds. When objects move toward us, their light is blue shifted to shorter wavelengths. When they move away, it's red shifted to longer wavelengths. By measuring these shifts with high precision, astronomers can determine radial velocities, the components of stellar motion along our line of sight. Dr. Burton Jones from the University of California, who developed advanced spectroscopic techniques, explains the precision required. Measuring galactic rotation requires detecting velocity differences of a few kilometers per second among stars separated by thousands of light years. This demands spectroscopic precision better than 1 part in 100,000, equivalent to detecting a person's walking speed from the moon. The 21-centimeter hydrogen line has proven crucial for mapping galactic rotation because it allows astronomers to observe neutral hydrogen gas throughout the galaxy, including regions obscured by interstellar dust. This radio emission penetrates dust clouds that block visible light, providing a clear view of gas motions throughout the entire galactic disk. Radio astronomy techniques using the 21-centimeter line can map velocity distributions across the entire Milky Way by observing how hydrogen gas rotates at different galactic radii. These observations reveal the characteristic signature of differential rotation, where gas closer to the galactic center moves faster than gas in the outer regions when measured relative to our solar system's motion. Proper motion measurements represent another crucial technique for studying galactic rotation. These observations detect the tiny angular motions of stars across the sky over periods of years or decades. While radial velocity measurements reveal motion along our line of sight, proper motions provide information about stellar movements perpendicular to our viewing direction. The Hipparcos satellite, launched in 1989, revolutionized proper motion measurements by providing precise positional data for over 100,000 stars from space, where observations aren't affected by atmospheric turbulence. Hipparcos measurements reveal detailed patterns of stellar motion in our local galactic neighborhood, confirming theoretical predictions about galactic rotation. The Gaia mission represents the current pinnacle of astrometric precision, measuring positions and proper motions for over 1 billion stars with accuracy better than 10 microseconds, equivalent to detecting the angular width of a 5-foot human hair from 1,000 kilometers away. These extraordinary measurements are revealing the detailed structure of stellar motions throughout the Milky Way. Parallax measurements provide the distance determinations essential for converting observed angular motions into actual velocities. Without accurate distances, proper motion measurements cannot be translated into the three-dimensional velocity information needed to understand galactic rotation patterns. The method of statistical parallax uses the motions of groups of stars to determine average distances, even when individual parallax measurements are not precise enough. This technique has been crucial for extending galactic rotation studies to greater distances than possible with direct parallax measurements. Cepheid variable stars serve as powerful distance indicators for measuring galactic rotation at large radii. These pulsating stars have well-established relationships between their pulsation periods and intrinsic luminosities, allowing astronomers to determine their distances by comparing apparent and intrinsic brightnesses. Globular clusters provide another approach to measuring galactic rotation by serving as test particles that orbit within the galaxy as gravitational field. By measuring the motions of these ancient stellar systems, astronomers can probe the gravitational potential and mass distribution of the Milky Way on large scales. The technique of kinematic distance determination uses galactic rotation models to estimate distances to objects with known radial velocities. This method assumes that gas and stars follow circular orbits around the galactic center, allowing astronomers to work backward from observed velocities to infer distances. Spiral arm tracers, including young massive stars and H2 regions, provide observational markers for studying how galactic rotation patterns relate to spiral structure. These objects are associated with ongoing star formation and help reveal how material flows through spiral arms over time. The local standard of rest calculation requires averaging the motions of nearby stars to determine our solar system's motion relative to the local galactic environment. This reference frame is essential for interpreting observations of galactic rotation and understanding how our cosmic neighborhood fits into larger galactic dynamics. Modern interferometric techniques can achieve angular resolution better than milliseconds by combining observations from multiple telescopes. These methods are particularly powerful for studying compact radio sources and masers associated with star-forming regions throughout the galaxy. Maser observations using water and methanol molecules provide extremely precise velocity measurements because these astronomical masers can be observed with very high spectral resolution. The compact nature of maser sources also makes them excellent probes of kinematic conditions in star-forming regions. The technique of secular parallax uses the solar system's motion around the galactic center to measure distances to very distant objects over time periods of decades. As our viewpoint changes due to galactic rotation, nearby objects exhibit apparent motions against the background of more distant stars. Computer simulations play an increasingly important role in interpreting galactic rotation measurements by modeling how observed kinematic patterns relate to underlying mass distributions and gravitational potentials. These simulations help astronomers understand which features in the data reflect galactic structure versus observational effects. Error analysis represents a crucial aspect of galactic rotation studies because the measurements require such extraordinary precision. Systematic errors in distance determinations, proper motion measurements, or radial velocity observations can significantly affect conclusions about galactic structure and dynamics. The combination of multiple measurement techniques provides the most robust determinations of galactic rotation parameters. By comparing results from different methods, spectroscopy, astrometry, and theoretical modeling, astronomers can identify and correct for systematic biases while improving overall measurement accuracy. Future measurement techniques promise even greater precision in studying galactic rotation. Next-generation space missions may achieve astrometric accuracy approaching 1 microsecond, while ground-based telescopes with adaptive optics systems continue to improve the precision of spectroscopic observations. Machine learning approaches are revolutionizing the analysis of large astronomical datasets, allowing researchers to identify subtle patterns in stellar motions that might indicate previously unknown aspects of galactic structure or dynamics. The development of three-dimensional mapping techniques using multiple distance indicators simultaneously is providing increasingly detailed views of how stellar populations with different ages and compositions participate in galactic rotation. Dr. Mark Reed from the Harvard-Smithsonian Center for Astrophysics reflects on measurement advances. Our ability to measure galactic rotation has improved by factors of thousands over the past few decades. What once required heroic observational efforts can now be accomplished routinely, allowing us to study galactic dynamics with unprecedented detail. The measurement methods that revealed the Milky Way as 515,000 mile-per-hour rotation demonstrate how astronomical observation techniques have evolved from simple positional measurements to sophisticated analyses of stellar motions in three-dimensional space, requiring international cooperation, advanced technology, and mathematical techniques that push the boundaries of measurement science. Understanding these measurement challenges provides appreciation for the extraordinary precision required to study galactic dynamics and reveals how continued technological advances promise to deepen our understanding of how galaxies like the Milky Way form, evolve, and maintain their organized rotation patterns over billions of years. Chapter 6. Spiral Secrets: The Milky Way. S rotation at 515,000 miles per hour creates one of the most beautiful and puzzling features in our galaxy. Spiral arms that sweep through the galactic disk like cosmic pinwheels, maintaining their structure for hundreds of millions of years despite the differential rotation that should have wound them up and destroyed them long ago. Understanding how these spiral patterns persist reveals fundamental principles about galactic dynamics and the role of density waves in organizing matter throughout the universe. Spiral arms represent regions of enhanced stellar and gas density that appear as bright, curved features when we observe our galaxy from within. These structures contain approximately 10 to 20% more stars and gas than the surrounding galactic disk, along with most of the galaxy's active star formation regions. The concentration of young, hot, blue stars in spiral arms creates the bright patterns we see when observing other spiral galaxies from great distances. The fundamental mystery of spiral arm persistence emerged when astronomers first calculated how differential rotation should affect these structures. If spiral arms were simply material features rotating with the galactic disk, differential rotation would wind them tighter and tighter over time. Within just a few rotation periods, roughly 500 million years, the arms should become so tightly wound that they would disappear entirely. Yet observations reveal that spiral galaxies throughout the universe maintain well-defined spiral patterns, many of which have persisted for billions of years. This spiral winding problem led astronomers to realize that spiral arms cannot be permanent material structures, but must instead represent waves or patterns that propagate through the galactic disk, independently of the rotation of individual stars and gas clouds. Dr. Bertil Lindblad and later Lin Shu developed the density wave theory that explains how spiral patterns can persist despite differential rotation. According to this theory, spiral arms represent pressure waves that propagate through the galactic disk at speeds different from the rotation velocities of individual stars. These density waves compress gas and trigger star formation as material flows through them, creating the bright spiral patterns we observe. The mathematics of spiral density waves involves complex relationships between wave frequencies, rotation velocities, and gravitational forces that shape how these patterns propagate through galactic disks. The waves travel at specific speeds that allow them to maintain coherent spiral structures despite the differential rotation that would destroy simple material arms. Resonance phenomena play crucial roles in spiral arm dynamics by determining where and how density waves can propagate through galactic disks. The Cartesian resonance occurs where the spiral pattern speed equals the local rotation velocity, while Lindblad resonances occur where the pattern frequency matches specific combinations of stellar orbital frequencies. The inner Lindblad resonance typically occurs near the galactic center and can drive bar formation, while the outer Lindblad resonance at larger radii helps terminate spiral arms and prevent them from extending indefinitely through the galactic disk. These resonances create preferred locations for various galactic structures and influence how spiral patterns evolve over time. Our solar system's location within the Milky Way spiral structure affects our cosmic environment in ways that may influence biological evolution on Earth. As we orbit the galactic center at 515,000 miles per hour, we periodically pass through spiral arms, exposing our solar system to enhanced levels of cosmic radiation and increased supernova rates that could affect Earth's climate and biosphere. The galactic habitable zone concept suggests that our location between spiral arms may be optimal for life because it provides protection from the intense radiation environment within spiral arms while ensuring access to the heavy elements produced by stellar nucleosynthesis in star-forming regions. This Goldilocks location may explain why complex life evolved on Earth. Magnetic fields play important roles in spiral arm physics by influencing how gas flows through density wave compression zones and affects star formation rates. The galactic magnetic field becomes compressed and amplified within spiral arms, creating conditions that can either promote or inhibit star formation depending on local conditions. Shock fronts associated with spiral density waves create some of the most dramatic examples of large-scale fluid dynamics in the universe. As gas encounters these compression waves while orbiting the galactic center, it experiences sudden changes in density, temperature, and velocity that trigger complex chemical and physical processes. The pitch angle of spiral arms, the angle at which they wind around the galactic center, provides information about the underlying gravitational potential and the properties of the density waves that create spiral structure. Tightly wound spirals typically indicate strong gravitational fields, while more open spirals suggest different mass distributions. Grand design spirals like the Milky Way exhibit well-defined, coherent spiral patterns that span the entire galactic disk. These structures require specific conditions to form and maintain, including appropriate mass distributions, rotation curves, and possibly the presence of central bars that drive spiral wave generation. The Milky Way's bar structure, a central elongated concentration of stars and gas, plays a crucial role in generating and maintaining our galaxy's spiral arms. Theoretical models suggest that bars create gravitational perturbations that launch spiral density waves that propagate outward through the galactic disk. Stellar feedback processes affect spiral arm evolution by injecting energy and momentum into the interstellar medium through supernova explosions and stellar winds. These processes can disrupt spiral structures locally while potentially triggering spiral wave formation through complex feedback mechanisms. The age of spiral patterns remains an active area of research, with some theories suggesting that spiral arms are transient features that form and dissipate over timescales of hundreds of millions of years, while others propose that spiral waves can persist for much longer periods under appropriate conditions. Spiral arm star formation occurs when density waves compress interstellar gas beyond critical thresholds, triggering gravitational collapse and the formation of new stellar systems. This process creates the chain of star-forming regions that trace out spiral arm patterns and provides the young stars that make spiral arms visible in other galaxies. The spacing between spiral arms reflects the wavelength of the underlying density waves and provides information about galactic mass distributions and rotation properties. Typical arm-to-arm separations range from several thousand to tens of thousands of light years, depending on galactic properties. Computer simulations of spiral arm dynamics have revealed complex interactions between density waves, gas dynamics, and star formation that create detailed predictions about how spiral patterns should evolve under different conditions. These simulations help astronomers understand observed spiral structures and predict their future evolution. The discovery of flocculent spiral patterns in some galaxies which appear more fragmented and chaotic than grand design spirals, suggests that multiple physical processes can create spiral-like structures through different mechanisms, including stochastic star formation and gravitational instabilities. Recent observations using the Gaia satellite have revealed detailed stellar motions within spiral arms that provide new tests of density wave theory. These measurements show how stellar velocities change as stars pass through spiral compression zones, confirming many theoretical predictions while revealing new complexities. The interaction between spiral arms and galactic bars creates complex dynamical environments that can drive gas inflows toward galactic centers, potentially fueling central black hole growth and affecting galaxy evolution over cosmic timescales. Environmental effects on spiral structure include interactions with neighboring galaxies, which can trigger or disrupt spiral patterns through gravitational torques and tidal forces. These interactions help explain why isolated galaxies often display different spiral characteristics than galaxies in dense cluster environments. Dr. Frank Hsu, who developed much of modern spiral wave theory, reflects on the significance of spiral arm physics. Understanding spiral arms reveals how galaxies organize matter into beautiful, large-scale patterns that persist for cosmic ages. These structures demonstrate how wave phenomena can create order and beauty on scales spanning tens of thousands of light years. The study of spiral secrets continues to reveal new aspects of galactic physics, from the role of dark matter in shaping spiral structure to the complex interactions between magnetic fields, turbulence, and density waves that determine how spiral patterns evolve over billions of years. Spiral arms represent one of nature's most spectacular examples of self-organizing systems, where simple physical laws governing gravity, fluid dynamics, and thermodynamics combine to create coherent structures that span galactic scales and persist for cosmological timescales, demonstrating how the universe creates beauty and order through the elegant application of fundamental physics. The spiral secrets embedded within our galaxy, as 515,000 mile-per-hour rotation, reveal how differential motion can create stable patterns rather than destroying them, showing how the Milky Way maintains its elegant spiral structure while participating in the cosmic dance of galactic evolution. Chapter 7. Central Engine at the heart of the Milky Way, as 515,000 mile-per-hour rotation, lies one of the most extreme objects in the universe. Sagittarius, a supermassive black hole containing over 4 million times the mass of our Sun compressed into a region smaller than our solar system. This central engine doesn't directly drive galactic rotation like a cosmic motor, but its enormous gravitational influence shapes the inner regions of our galaxy while providing crucial insights into how galactic dynamics operate on the largest scales. The discovery of Sagittarius A** required decades of patient observation because it is located 26,000 light-years away behind dense clouds of interstellar dust that block visible light from the galactic center. Radio astronomy first revealed the presence of an unusual compact radio source in the constellation Sagittarius, but determining its true nature required sophisticated infrared and radio interferometry techniques that could peer through the dusty galactic plane. Dr. Reinhard Genzel and Andrea Ghez, who shared the 2020 Nobel Prize in Physics for their work, led parallel research teams that tracked individual stars orbiting near the galactic center for over 2 decades. Their observations revealed stars moving at velocities exceeding 20,000 kilometers per second, nearly 7% the speed of light, in highly elliptical orbits around an invisible massive object. The orbital motions of these stars provided direct evidence for the black hole S-mass through applications of Kepler's laws of orbital mechanics. By measuring orbital periods and distances for stars like S2, which has an orbital period of 16 years and approaches within 120 astronomical units of the black hole, astronomers could calculate that the central object contains 4.15 million solar masses within a region no larger than about 60 astronomical units. The gravitational influence of Sagittarius A** extends throughout the inner regions of the galaxy, affecting stellar orbits and gas dynamics within the central few thousand light years. While this influence doesn't directly drive the 515,000 mile/hour rotation observed in our solar system's galactic neighborhood, it plays crucial roles in organizing galactic structure and evolution. The supermassive black hole sits at the center of the galaxy's gravitational potential well, representing the deepest point in the Milky Way's gravitational field. This central concentration of mass helps stabilize galactic rotation patterns by providing a gravitational anchor that maintains the overall symmetry of galactic dynamics over billions of years. Sagittarius A** exhibits relatively low activity compared to the supermassive black holes found in some other galaxies. It currently accretes matter at rates that produce luminosities only about 1 billion times dimmer than its theoretical maximum, suggesting that our galaxy's central engine is in a relatively quiet state compared to active galactic nuclei observed in distant galaxies. The accretion disk around Sagittarius * extends from the black hole's event horizon, the boundary beyond which nothing can escape, to distances of several hundred astronomical units. Material in this disk spirals inward while radiating energy at radio, infrared, and X-ray wavelengths, providing observational signatures that allow astronomers to study black hole physics in unprecedented detail. The Event Horizon Telescope collaboration achieved a remarkable feat of directly imaging the shadow of Sagittarius * in 2022, revealing the silhouette of the black hole's event horizon against the bright emission from its accretion disk. This image confirmed theoretical predictions about black hole appearance while providing new tests of general relativity in the strong field regime. Stellar formation processes near the galactic center operate under extreme conditions created by the supermassive black hole as gravitational influence and the high-energy radiation environment. Despite these challenging conditions, star formation continues within a few light-years of Sagittarius *, creating young, massive stars that live brief, violent lives before exploding as supernovas. The galactic center stellar cluster contains an unusual population of young, massive stars whose formation mechanism remains mysterious. These stars shouldn't be able to form so close to the supermassive black hole due to strong tidal forces, leading to theories that they either formed farther out and migrated inward, or formed through exotic processes unique to the galactic center environment. Relativistic jets, though not currently observed from Sagittarius A*, may have been active in the past and could become active again if the black hole's accretion rate increases. Such jets could inject enormous amounts of energy into the galactic environment and influence star formation, gas dynamics, and chemical evolution throughout the inner galaxy. The measurement of stellar orbits near Sagittarius A* has provided some of the most precise tests of Einstein's general relativity in strong gravitational fields. The star S2's closest approach to the black hole in 2018 allowed astronomers to detect the gravitational redshift of its light and the relativistic precession of its orbit, confirming general relativistic predictions with extraordinary accuracy. Gravitational wave emission from the Sagittarius A* system could potentially be detected by future space-based gravitational wave observatories like LISA. While individual stellar orbits don't produce detectable signals, the inspiral and merger of objects into the black hole could generate gravitational waves that carry information about black hole physics and galactic center dynamics. The interaction between Sagittarius A* and the galaxy's bar structure may influence how material flows toward the galactic center and affects the black hole's feeding rate. Galactic bars can drive gas inflows that transport material from the outer galactic disk to the central regions, potentially triggering periods of enhanced black hole activity. Historical observations of the galactic center region suggest that Sagittarius A** may have been much more active in the past. Evidence for past activity includes high-energy bubbles extending above and below the galactic plane, known as Fermi bubbles, which may have been created by jets or outflows from the central black hole millions of years ago. The role of magnetic fields near Sagittarius A* affects how matter spirals into the black hole and influences the emission properties of the accretion flow. Strong magnetic fields can transport angular momentum outward while allowing matter to fall inward, playing crucial roles in black hole accretion physics. Tidal disruption events occur when stars venture too close to Sagittarius A* and are torn apart by tidal forces. These dramatic events can briefly increase the black hole's luminosity and provide opportunities to study black hole physics under extreme conditions while revealing information about the stellar population in the galactic center. The supermassive black hole's influence on galactic chemical evolution occurs through its effects on star formation, stellar evolution, and gas dynamics in the central regions. Material processed near the galactic center can eventually mix throughout the galaxy, carrying signatures of the extreme physical processes that occur near supermassive black holes. Coevolution between supermassive black holes and their host galaxies represents an active area of research that connects galactic center physics to large-scale galaxy formation and evolution. Correlations between black hole masses and galactic properties suggest that black hole growth and galactic evolution are intimately connected through feedback processes. The measurement of frame-dragging effects near Sagittarius A* may become possible with future observational techniques. This general relativistic effect, where the black hole's rotation drags spacetime around it, should influence the orbits of nearby stars and provide additional tests of Einstein's theory. Intermediate mass black holes may exist within the Sagittarius A* system, potentially formed through the collapse of massive star clusters or the merger of smaller black holes. Detecting these objects would provide insights into black hole formation mechanisms and the hierarchical growth of supermassive black holes. The galactic center environment provides a unique laboratory for studying physics under extreme conditions, including strong gravitational fields, high radiation densities, and relativistic particle velocities. Observations of this region continue to reveal new phenomena that challenge our understanding of black hole physics and galactic dynamics. Future observations of Sagittarius A*, using next-generation instruments, promise to reveal even more detailed information about black hole physics and the central engine's role in galactic evolution. These observations will help answer fundamental questions about how supermassive black holes form, grow, and influence their galactic environments. Dr. Fariel Zil from the University of Arizona, who studies black hole physics, reflects on the central engine's significance. Sagittarius A* serves as our closest laboratory for studying supermassive black hole physics and provides unique insights into how these extreme objects influence galactic structure and evolution on the largest scales. The central engine of the Milky Way demonstrates how supermassive black holes, despite their relatively small size compared to galactic scales, can influence the structure, dynamics, and evolution of entire galaxies through gravitational effects, energy injection, and complex feedback processes that operate over billions of years, and affect the 515,000 mile-per-hour rotation that carries our solar system through the cosmos. Chapter 8. Collision Course: The Milky Way's Current. 515,000 mile-per-hour rotation represents just one phase in our galaxy's dynamic evolution, because we are currently on a collision course with our nearest galactic neighbor, the Andromeda Galaxy. This cosmic collision, predicted to occur in approximately 4.5 billion years, will fundamentally alter galactic dynamics and create an entirely new galactic system with completely different rotation patterns and structural characteristics. The discovery of our galaxy's collision course with Andromeda emerged from precise measurements of the neighboring galaxy's motion through space. Using the Hubble Space Telescope to measure tiny proper motions of stars within Andromeda over periods of several years, astronomers determined that the galaxy is approaching us at approximately 250,000 miles per hour while moving sideways at much slower speeds. Dr. Roland van der Marel from the Space Telescope Science Institute led the team that definitively confirmed the collision trajectory. Their analysis revealed that Andromeda's motion through space will bring it into direct collision with the Milky Way rather than causing it to pass by harmlessly. This head-on collision will occur despite the enormous distances involved. Andromeda is currently 2.5 million light-years away. The approaching collision will dramatically affect both galaxies' rotation patterns billions of years before they actually merge. Gravitational interactions between the two galaxies will begin to distort their spiral structures when they're still separated by hundreds of thousands of light-years, creating tidal streams, warping galactic disks, and triggering bursts of star formation. Computer simulations of galactic collisions revealed that the merger process will unfold over several billion years, involving multiple close encounters before the galaxies finally settle into a stable configuration. During these encounters, gravitational forces will fling stars into new orbits, completely reshuffling the organized rotation patterns that currently characterize both galaxies. The ultimate result of the collision will be the formation of a new elliptical galaxy, informally dubbed Milkomeda or Milktromeda. This merged system will have completely different dynamics from either parent galaxy, with stars following complex three-dimensional orbits rather than the organized disk rotation that currently carries our solar system around the galactic center at 515,000 miles per hour. Our solar system's fate during this cosmic collision depends on complex gravitational dynamics that are difficult to predict precisely. While the Sun and Earth will likely survive the merger process physically intact, they may be flung into the outer regions of the merged galaxy or follow completely different orbital paths through the new galactic structure. The collision process will trigger massive bursts of star formation as gas clouds in both galaxies collide and compress. These starbursts will consume much of the available gas for star formation, potentially ending the era of steady star formation that has characterized both galaxies for billions of years and fundamentally altering the galactic environment. Supermassive black holes at the centers of both galaxies will eventually merge during the collision, creating an even more massive black hole that could weigh over 100 million times the mass of our Sun. This black hole merger will generate gravitational waves and may trigger periods of intense activity that could affect star formation and galactic evolution throughout the merged system. The Large and Small Magellanic Clouds, satellite galaxies currently orbiting the Milky Way, will also participate in this cosmic collision. These smaller galaxies may be disrupted entirely by the gravitational chaos of the merger, with their stars scattered throughout the new galactic system or possibly ejected into intergalactic space. Tidal forces during the collision will create spectacular stellar streams and bridges connecting the merging galaxies, similar to features observed in other galactic collisions throughout the universe. These tidal features can extend for hundreds of thousands of light years and persist for billions of years after the collision is complete. The collision timeline begins with subtle gravitational interactions that are already affecting both galaxies, continues through a series of close encounters that will reshape galactic structure, and culminates in the final merger that creates the new elliptical galaxy. Each phase of this process will alter galactic dynamics and the motion of individual stellar systems. Environmental effects of the collision will include changes in cosmic ray fluxes, supernova rates, and stellar formation activity that could affect planetary atmospheres and biological evolution throughout both galactic systems. The increased density of stellar encounters may also affect the stability of planetary orbits over long timescales. Observational evidence for the upcoming collision includes detailed measurements of Andromeda's proper motion, analysis of existing tidal features between the galaxies, and studies of the local group's overall gravitational dynamics. These observations provide increasingly precise predictions about collision timing and dynamics. The role of dark matter in galactic collisions is crucial because dark matter halos are the dominant mass components of both galaxies. The interaction between these dark matter structures will largely determine the merger dynamics and the final properties of the merged system. Similar galactic mergers observed throughout the universe provide insights into what we can expect from the Milky Way Andromeda collision. These observations reveal that major mergers transform spiral galaxies into elliptical systems while triggering massive starbursts and potentially activating central supermassive black holes. The impact on galactic habitable zones during the collision remains an active area of research. While the increased stellar density and activity may create hazardous radiation environments in some regions, it could also enrich the interstellar medium with heavy elements and potentially create new opportunities for planet formation. Stellar dynamics during galactic mergers involve complex three-body and many-body gravitational interactions that can scatter stars into highly elliptical orbits or even eject them from the galaxy entirely. These processes will completely reorganize the orderly rotation patterns that currently characterize both galactic disks. The preservation of galactic substructure during mergers depends on the mass ratios and approach velocities of the colliding systems. Some stellar associations and clusters may survive the merger process intact while being relocated to different regions of the new galactic system. Energy dissipation during the collision occurs primarily through gravitational interactions and gas dynamics rather than direct stellar collisions. Despite the enormous numbers of stars involved, actual stellar collisions will remain extremely rare due to the vast distances between individual stars. The formation of the new galactic center will involve complex dynamics as the two supermassive black holes spiral toward each other while gas flows toward the merger site. This process may create an active galactic nucleus phase that could last for millions of years. Future observations will continue to refine our understanding of the collision timeline and dynamics. Next generation space telescopes and ground-based observatories will provide increasingly detailed measurements of both galaxy structures and motions. Theoretical modeling of galactic collisions continues to improve as computational capabilities advance and our understanding of galaxy formation physics evolves. These simulations help predict the detailed consequences of the collision for stellar populations, gas dynamics, and overall galactic evolution. The long-term stability of the merged system will depend on how effectively energy is dissipated during the collision and whether the final configuration represents a stable equilibrium. Most merger simulations suggest that the final elliptical galaxy will remain stable for many billions of years. Comparative studies of galactic mergers at different redshifts reveal that such collisions were more common in the early universe and played crucial roles in galaxy formation and evolution. The Milky Way Andromeda collision represents a relatively late example of major galaxy merger activity. Dr. Frank van den Bosch from Yale University reflects on the collision's significance. The upcoming merger with Andromeda will mark the end of our galaxy's current phase of evolution and the beginning of a completely new chapter in the history of our cosmic neighborhood. It represents one of the most dramatic changes our galactic environment will ever experience. The collision course that will eventually end the Milky Way's current 515,000 mile-per-hour rotation demonstrates how galactic evolution operates over cosmic timescales, transforming the organized structures we observe today into completely different configurations that reflect the ongoing dance of gravity and dynamics that shapes the largest structures in the universe over billions of years. Chapter 9. Cosmic perspective. The Milky Way's rotation at 515,000 miles per hour represents just one component of a complex hierarchy of cosmic motions that carry our solar system through space at combined velocities that challenge human comprehension. Understanding our complete cosmic motion requires stepping back to view the universe from the largest possible perspective, where galaxies themselves are just small components in vast cosmic structures that span hundreds of millions of light years and evolve over billions of years. Our solar system participates in at least 4 distinct types of motion simultaneously. Earth orbits the Sun at 67,000 miles per hour. The Sun orbits the galactic center at 515,000 miles per hour. The Milky Way moves through the local group of galaxies at approximately 185,000 miles per hour. And the local group itself travels toward the Virgo cluster at roughly 1.3 million miles per hour. When all these motions are combined, our total cosmic velocity exceeds 2 million miles per hour. But even this enormous speed represents only our motion relative to nearby cosmic structures. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a reference frame for measuring our motion relative to the observable universe as a whole. Relative to this cosmic reference frame, our local group moves at approximately 1.4 million miles per hour toward a region of space, dominated by massive galaxy clusters. Dr. Alan Dressler from the Carnegie Institution, who discovered the cosmic motion toward what he termed the Great Attractor, explains the scale of cosmic flows. Our galaxy's rotation is just one component in a vast hierarchy of motions that extends from planetary orbits to the large-scale flow of matter throughout the observable universe. Understanding these motions reveals how structure forms and evolves on the largest cosmic scales. The Great Attractor represents a massive concentration of galaxies and dark matter located approximately 200 million light-years away in the direction of the constellation Hydra. This structure contains the mass equivalent of tens of thousands of galaxies and generates gravitational forces strong enough to influence galactic motions across hundreds of millions of light-years. Beyond the Great Attractor lies an even larger structure called the Shapley supercluster, which contains thousands of galaxies distributed across a region spanning over 400 million light-years. The gravitational influence of this enormous concentration of matter affects galactic motions throughout our cosmic neighborhood and may be responsible for the large-scale flows observed in galaxy surveys. The local supercluster, also known as the Virgo supercluster, encompasses our local group, along with thousands of other galaxies distributed in a flattened structure, roughly 110 million light-years across. Our location within this supercluster affects our cosmic motion and provides context for understanding how galaxy groups and clusters organize themselves on large scales. Recent discoveries have revealed that superclusters are organized into even larger structures called cosmic filaments and walls that span hundreds of millions of light-years. These features represent the largest coherent structures in the observable universe and create the cosmic web that governs how matter and energy flow throughout space. The concept of cosmic expansion adds another layer of complexity to understanding our cosmic motion. Due to the expansion of the universe itself, distant galaxies recede from us at velocities that increase with distance according to Hubble's law. This expansion motion is separate from the peculiar velocities caused by gravitational attraction and affects how we interpret observations of cosmic structure. Dark energy, the mysterious force driving cosmic expansion, influences motion patterns on the largest scales while having negligible effects on smaller structures like galaxies and galaxy clusters. Understanding how dark energy affects cosmic evolution provides crucial context for interpreting the large-scale motions that carry our galaxy through space. The Laniakea supercluster represents an even larger structure that encompasses our local supercluster along with several neighboring superclusters in a region spanning over 500 million light-years. This vast structure was identified through analysis of galaxy motions that revealed coherent flow patterns extending across enormous cosmic distances. Cosmic voids, enormous regions of space with very low galaxy densities, also influence large-scale motions by creating pressure gradients that affect how matter flows through the cosmic web. These voids can span hundreds of millions of light-years and represent some of the most underdense regions in the observable universe. The observation of cosmic flows requires sophisticated techniques for measuring galaxy distances and velocities across enormous ranges. These measurements reveal how gravitational forces propagate across cosmic scales and provide insights into the distribution of matter throughout the universe. Peculiar velocities, the motions of galaxies relative to the smooth Hubble flow, provide information about mass distributions and gravitational fields on scales ranging from galaxy clusters to superclusters. These deviations from uniform expansion reveal how cosmic structure affects galactic motions. The cosmic rest frame defined by the cosmic microwave background provides a universal reference for measuring absolute motions throughout the universe. This frame reveals that our galaxy participates in large-scale flows that reflect the influence of massive structures distributed across hundreds of millions of light-years. Cosmic timescales associated with large-scale motions span billions of years, comparable to the age of the universe itself. The motions we observe today reflect gravitational influences that have been operating since the early epochs of cosmic structure formation, when the universe was much smaller and denser than today. The role of dark matter in cosmic flows is crucial because dark matter comprises roughly 85% of all matter and dominates gravitational dynamics on large scales. Understanding how dark matter structures evolve and interact provides key insights into the forces that drive cosmic motions. Computer simulations of cosmic structure formation reveal how the observed patterns of cosmic motion emerged from tiny density fluctuations in the early universe. These simulations show how gravitational instability amplified small perturbations into the vast structures that dominate cosmic dynamics today. The measurement of cosmic flows provides tests of fundamental physics, including general relativity and alternative theories of gravity. Deviations from predicted flow patterns could indicate new physics operating on cosmic scales or reveal previously unknown massive structures. Environmental effects of cosmic motion include variations in cosmic ray fluxes, changes in the local density of intergalactic medium, and potential influences on galactic evolution processes. These effects operate over timescales much longer than human civilization, but may influence galactic habitability over cosmic time. The future evolution of cosmic flows depends on the continued expansion of the universe and the influence of dark energy. As cosmic expansion accelerates, large-scale structures will become increasingly isolated, eventually ending the era of cosmic flow and large-scale structure formation. Observational projects like the Cosmic Flow Surveys continue to map galaxy motions across larger volumes and greater distances, revealing new aspects of cosmic structure and the forces that drive galactic motions throughout the observable universe. The connection between local galactic dynamics and cosmic scale physics demonstrates how the Milky Way's rotation at 515,000 miles per hour fits into a vast hierarchy of motions that extends from planetary orbits to the largest structures in the universe. Philosophical implications of cosmic motion include questions about absolute versus relative motion, the nature of cosmic time, and humanity's place in a universe characterized by constant motion on all scales, from atomic to cosmic. The study of cosmic perspectives reveals that the concept of stationary has no meaning in a universe where everything is in motion relative to everything else, from subatomic particles to galactic superclusters, creating a dynamic cosmos where change and motion are fundamental characteristics. Dr. Brent Tully from the University of Hawaii, who mapped the Laniakea supercluster, reflects on cosmic motion. Understanding our place in the cosmic web of motions reveals that we're participants in the largest scale dynamics of the universe. Our galaxy's rotation is just one thread in an enormous tapestry of motion that connects us to cosmic evolution itself. The cosmic perspective on the Milky Way's 515,000 mile-per-hour rotation reveals how local galactic dynamics participate in universal processes that span scales from individual galaxies to the largest structures in the observable universe, demonstrating how cosmic evolution creates hierarchical systems where motion and structure emerge from the gravitational dance of matter and energy across cosmic space and time. Chapter 10. Formation Story. Milky Way's current rotation at 515,000 miles per hour represents the culmination of a 13.6 billion year formation process that transformed a primordial cloud of hydrogen and helium into one of the universe's most complex gravitational structures. Understanding how our galaxy acquired its mass, structure, and rotation patterns reveals fundamental principles about galaxy formation while providing insights into how cosmic evolution creates the organized motions we observe throughout the universe today. The formation story begins approximately 400 million years after the Big Bang, when the universe had cooled enough to allow the first structures to collapse under their own gravity. In regions where dark matter had accumulated to densities slightly higher than the cosmic average, gravitational forces began to overcome cosmic expansion, creating the first dark matter halos that would eventually host galaxies like the Milky Way. These primordial dark matter halos grew through accretion and mergers, gradually assembling the mass needed to capture and retain ordinary matter. When halos reached masses equivalent to several billion solar masses, they became capable of attracting and holding on to the hot gas that filled the early universe, setting the stage for the first episodes of star formation. Dr. James Bullock from the University of California, Irvine, who studies galaxy formation, explains the process. Galaxy formation required dark matter to create gravitational scaffolding that could capture ordinary matter and organize it into rotating disks. Without dark matter, the gravity from ordinary matter alone would have been insufficient to build galaxies during the early epochs of cosmic history. The angular momentum that drives the Milky Way's rotation originated from tidal torques generated by neighboring dark matter structures in the early universe. As our proto-galaxy's dark matter halo grew, gravitational interactions with surrounding mass concentrations imparted spin that became locked into the system's rotational dynamics. The first stars in our galaxy formed from pristine hydrogen and helium gas approximately 13 billion years ago, when the universe was less than 1 billion years old. These population 3 stars were much more massive than typical stars today and lived brief, violent lives before exploding as supernovas, enriching the early galactic environment with the first heavy elements. Subsequent generations of star formation incorporated these heavy elements, creating population 2 stars with enhanced metallicities that formed the galactic halo and thick disk components. These stellar populations exhibit the kinematic signatures of their formation epochs, with older stars showing more random orbits and younger stars participating more fully in organized galactic rotation. The assembly of the Milky Way's stellar mass occurred through 2 primary mechanisms: in situ star formation within the forming galactic disk and accretion of smaller satellite galaxies that contributed preformed stellar populations. Recent observations suggest that roughly half of our galaxy's stellar mass formed within the main galactic structure, while the other half was acquired through mergers and accretion events. The formation of the galactic disk required efficient cooling of hot gas within the dark matter halo, allowing material to settle into a rotating, flattened configuration. This cooling process was facilitated by heavy elements produced by early generations of stars, which radiate energy more efficiently than pure hydrogen and helium. Major merger events early in the Milky Way's history significantly affected galactic structure and rotation patterns. The Gaia-Enceladus merger, which occurred approximately 8 to 10 billion years ago, brought roughly 25% of our galaxy's current stellar mass and fundamentally altered the structure of the early galactic disk. Chemical evolution during galaxy formation created the metallicity gradients and abundance patterns observed throughout the Milky Way today. Successive generations of star formation, supernova explosions, and stellar winds redistributed heavy elements throughout the galaxy, creating the chemical complexity needed for planet formation and biological evolution. The role of supermassive black hole growth during galaxy formation remains an active area of research. The central black hole likely formed during the earliest phases of galactic assembly and co-evolved with the galaxy through feedback processes that regulated star formation and influenced structural evolution. Feedback mechanisms from stellar winds, supernova explosions, and active galactic nucleus activity played crucial roles in regulating galaxy formation by ejecting gas from star-forming regions and preventing runaway star formation that could have consumed all available gas in the early universe. The timing of different formation phases affected how various galactic components acquired their current properties. The halo formed first through chaotic accretion processes, followed by the thick disk during a period of enhanced merger activity, and finally the thin disk during the most recent epochs of galactic evolution. Environmental influences on galaxy formation included the effects of cosmic reionization, which heated intergalactic gas and affected cooling processes, and interactions with neighboring galaxies that influenced merger rates and gas accretion patterns. The local group environment provided specific conditions that affected Milky Way formation, including gravitational interactions with Andromeda and other nearby galaxies that influenced our galaxies, orbital angular momentum and structural evolution over cosmic time. Observational evidence for the formation history comes from stellar archaeology, the study of ancient stars whose chemical compositions preserve information about early galactic conditions. These stellar fossils reveal details about the star formation history, chemical evolution, and merger events that shaped our galaxy. The globular cluster system provides additional constraints on galaxy formation models because these ancient stellar systems formed during the earliest epochs of galactic assembly. Their spatial distribution, chemical compositions, and kinematics reflect conditions during the Milky Way's youth. Satellite galaxies like the Magellanic Clouds continue the accretion process that built our galaxy, demonstrating that galaxy formation is an ongoing process rather than a completed event. These systems will eventually merge with the Milky Way, adding their mass and angular momentum to our galactic system. Theoretical models of galaxy formation must explain how systems like the Milky Way acquired their specific masses, sizes, rotation velocities, and structural characteristics. These models require detailed understanding of dark matter physics, gas dynamics, stellar feedback, and cosmological boundary conditions. The Lambda-CDM cosmological model provides the framework for understanding galaxy formation within the context of cosmic structure formation. This model successfully predicts many observed properties of galaxies like the Milky Way, while facing challenges in explaining some detailed aspects of galactic structure. Simulation studies of galaxy formation use supercomputers to model the complex physics involved in building galaxies from initial cosmological conditions. These simulations reveal how small-scale processes like star formation and stellar feedback affect large-scale galactic properties, like rotation curves and structural morphology. The formation of spiral structure likely occurred after the main galactic disk had assembled through processes involving gravitational instabilities, bar formation, and density wave propagation. The timing and mechanisms of spiral arm formation continue to be active areas of research. The acquisition of angular momentum during galaxy formation determine the final rotation velocity and disk size of systems like the Milky Way. Understanding how galaxies acquire and retain angular momentum remains one of the key challenges in galaxy formation theory. Recent discoveries have revealed that galaxy formation was more complex and extended than previously thought, with significant stellar mass assembly continuing to relatively recent epochs. This extended formation timeline helps explain the diversity of stellar populations observed in the modern Milky Way. Dr. Amina Helmi from the University of Groningen, who studies galactic archaeology, reflects on the formation story. The Milky Way's rotation patterns preserve the memory of billions of years of galactic evolution. By studying stellar motions and chemical compositions, we can reconstruct the complex history that created our cosmic home. The formation story of the Milky Way reveals how cosmic evolution transforms simple initial conditions into complex, organized systems capable of supporting the 515,000 mile/hour rotation that carries our solar system through space, demonstrating how fundamental physics creates beautiful, stable structures through processes that operate over cosmic timescales and scales spanning orders of magnitude in mass, distance, and time. Understanding galaxy formation provides context for appreciating the extraordinary achievement represented by our galaxy's organized rotation, a stable, complex system that has maintained coherent dynamics for billions of years while continuously evolving through accretion, star formation, and internal dynamical processes. Chapter 11. Universal Context. The Milky Way's rotation at 515,000 miles per hour places our galaxy within a vast cosmic context where similar rotational motions characterize billions of other galaxies throughout the observable universe. Understanding how galactic rotation patterns vary across different galaxy types, cosmic epochs, and environments reveals fundamental principles about how gravitational systems organize matter and energy, while providing insights into the universal processes that create rotating cosmic structures. Spiral galaxies like the Milky Way represent just one category among the diverse population of rotating galaxies that populate the universe. These disk galaxies exhibit rotation patterns similar to our own, with velocities typically ranging from 100 to 500 kilometers per second, depending on galactic mass, size, and dark matter content. The remarkable consistency of these rotation patterns across billions of galaxies demonstrates that galactic rotation represents a fundamental mode of cosmic structure formation. Elliptical galaxies, which form primarily through major merger events, exhibit completely different rotation characteristics from spiral systems. These galaxies often show complex three-dimensional velocity patterns where stars follow elongated orbits rather than organized circular motions. However, many ellipticals do exhibit net rotation, with rotation velocities generally lower than comparable mass spiral galaxies. Dr. Marla Giha from Yale University, who studies galaxy kinematics across cosmic time, explains the diversity. Galactic rotation patterns reflect the formation histories and environmental conditions experienced by different galaxy types. Studying this diversity reveals how cosmic evolution creates the range of rotating systems we observe throughout the universe. The Tully-Fisher relation represents one of the most important scaling laws in galaxy science, linking rotation velocities to galactic luminosities and masses. This relationship suggests that faster rotating galaxies contain more stars and dark matter, reflecting fundamental connections between galactic rotation and the efficiency of star formation and mass assembly processes. Dwarf galaxies, which represent the most common galaxy type in the universe, exhibit rotation patterns that often deviate from larger systems. Many dwarf galaxies show evidence for dark matter domination even more extreme than in systems like the Milky Way, with rotation curves that remain flat to large radii despite containing relatively few stars. The study of galactic rotation at high redshift, observations of distant galaxies seen as they were billions of years ago, reveals how rotation Patterns have evolved over cosmic time. Early galaxies often show more chaotic kinematics and higher velocity dispersions, reflecting the more turbulent conditions that characterize galaxy formation in the early universe. Gravitational lensing observations provide unique opportunities to study galactic rotation in distant systems by magnifying background galaxies and allowing detailed kinematic studies at cosmological distances. These observations revealed that organized galactic rotation was established surprisingly early in cosmic history, within the first few billion years after the Big Bang. The role of environment in shaping galactic rotation patterns becomes evident when comparing galaxies in different cosmic settings. Galaxies in dense cluster environments often show truncated rotation curves and disturbed kinematics due to interactions with neighboring systems and the hot intracluster medium. Ultra-diffuse galaxies represent an extreme population characterized by very low surface brightnesses despite having sizes comparable to the Milky Way. These enigmatic systems often exhibit rotation velocities consistent with massive dark matter halos, suggesting they represent failed galaxies that never efficiently converted their dark matter mass into stars. The discovery of massive galaxies at high redshift with rotation velocities exceeding 500 kilometers per second demonstrates that the universe was capable of producing rapidly rotating systems even during early cosmic epochs. These observations challenge models of galaxy formation that predict more gradual assembly of galactic mass and angular momentum. Interacting galaxy pairs provide natural laboratories for studying how galactic rotation responds to external gravitational perturbations. Tidal forces during galaxy encounters can enhance or suppress rotation while triggering starbursts and fundamentally altering galactic structure and dynamics. The cosmic web environment affects galactic rotation through large-scale tidal forces and the availability of gas for accretion. Galaxies aligned with cosmic filaments may experience enhanced accretion and different rotation properties compared to systems in cosmic voids or other environments. Simulation studies of galaxy formation in cosmological contexts reveal how the universal properties of dark matter and cosmological parameters determine the statistical distributions of galactic rotation velocities observed across different cosmic epochs and environments. Active galactic nuclei can influence rotation patterns in their host galaxies through powerful outflows and jets that inject energy and momentum into galactic disks. These feedback processes may suppress or enhance rotation depending on the geometry and energy of the outflows. The measurement of galactic rotation across cosmic time requires sophisticated observational techniques that can detect kinematic signatures in extremely distant and faint systems. Recent advances in integral field spectroscopy and adaptive optics have revolutionized our ability to study rotation in high redshift galaxies. Low surface brightness galaxies often exhibit extended rotation curves that provide crucial tests of dark matter models and alternative gravity theories. These systems contain substantial dark matter halos while having relatively few stars, creating ideal conditions for studying dark matter physics. The correlation between galactic rotation and other galaxy properties, including stellar mass, metallicity, and star formation rate, reveals how rotation affects the physical processes that govern galaxy evolution over cosmic time. Satellite galaxy systems around massive galaxies like the Milky Way exhibit their own rotation patterns that reflect the gravitational influence of their hosts while providing insights into how substructure forms and survives within larger galactic halos. The study of galactic rotation in different galaxy morphologies reveals how various formation mechanisms, mergers, accretion, secular evolution, affect the final kinematic properties of galactic systems across the universe. Cosmic variance in galactic rotation properties reflects the stochastic nature of galaxy formation within the cosmic web. Understanding this variance requires large statistical samples and careful consideration of selection effects in galaxy surveys, the evolution of the fundamental plane and other scaling relations involving galactic rotation provides insights into how the universe's expansion and changing density affect galaxy formation efficiency over cosmic time. Future observational facilities promise to extend studies of galactic rotation to even higher redshifts and fainter systems, potentially revealing the earliest epochs of organized rotation in the universe and constraining models of primordial galaxy formation. The universality of galactic rotation patterns suggests that the same physical processes, gravitational collapse, angular momentum conservation, and dark matter dynamics, operate throughout the cosmos to create rotating galactic systems with remarkably consistent properties. Comparative studies of galactic rotation in different cosmological simulations help constrain fundamental parameters like dark matter properties, feedback efficiencies, and the influence of dark energy on structure formation processes. The connection between galactic rotation and cosmic chemical evolution reflects how rotating systems mix heavy elements and regulate star formation, affecting the cosmic abundance patterns that determine planet formation and habitability across the universe. Machine learning approaches applied to large galaxy surveys are revealing subtle patterns in rotation properties that provide new insights into galaxy formation physics and the role of environment in shaping galactic evolution. The study of counter-rotating systems and kinematically decoupled components in galaxies reveals how complex merger histories can create exotic rotation patterns that deviate from simple disk rotation models. Environmental quenching mechanisms that suppress star formation in dense environments also affect galactic rotation by altering gas content and changing the balance between stellar and dark matter contributions to galactic dynamics. Dr. Peter Van Dockum from Yale University reflects on the universal context. Studying galactic rotation across cosmic time and environment reveals that the Milky Way represents just one example of how the universe creates rotating galactic systems. Understanding this diversity helps us appreciate both the universality and uniqueness of our cosmic home. The universal context of galactic rotation demonstrates that the Milky Way's 515,000 mile-per-hour rotation participates in cosmic processes that operate throughout the observable universe, creating billions of similar rotating systems while revealing how local galactic properties connect to universal principles of structure formation, dark matter physics, and cosmic evolution that span the entire history of the universe from the Big Bang to the present day. Understanding how galactic rotation fits into the universal context provides perspective on both the commonality and specialness of our galactic home, revealing how fundamental physics creates organized rotating systems throughout the cosmos while creating the specific conditions that allowed our solar system and life on Earth to develop within one particular example of these cosmic pinwheels. Throughout our journey into the cosmic mechanics of galactic rotation, we've discovered that the Milky Way's incredible 515,000 mile-per-hour motion represents far more than just another astronomical measurement. It embodies fundamental principles about how gravity organizes matter across cosmic scales, how invisible dark matter dominates universal dynamics, and how our entire cosmic environment participates in motions that dwarf any velocity achievable through human technology. Perhaps the most profound revelation is recognizing that this extraordinary speed isn't unusual or extreme. It's precisely what's required to maintain the gravitational balance that keeps our galaxy stable over billions of years. The 515,000 miles per hour represents the perfect velocity needed to prevent our solar system from spiraling into the galactic center or flying off into intergalactic space, demonstrating how cosmic evolution creates remarkably fine-tuned systems through the elegant application of fundamental physics. The discovery that invisible dark matter drives galactic rotation has revolutionized our understanding of cosmic composition and revealed that the universe is but the universe, primarily made of substances we can't see, touch, or directly detect. This humbling realization reminds us that our scientific understanding remains incomplete and that the cosmos contains mysteries that challenge our most basic assumptions about the nature of matter and energy. Understanding how stellar traffic flows within our galaxy's rotation reveals a dynamic, ever-changing environment where hundreds of billions of stars follow complex orbital paths while maintaining overall coherence across scales spanning tens of thousands of light-years. This cosmic choreography demonstrates how individual motions can combine to create stable, long-term structures that persist for timescales far exceeding human civilization. The sophisticated measurement techniques required to determine galactic rotation showcase humanity's growing technological capability to understand cosmic phenomena through mathematical physics and precision observation. From early spectroscopic studies to modern space-based astrometry, these measurements represent some of the most challenging and precise accomplishments in the history of science. The persistence of spiral arms despite differential rotation reveals how wave phenomena can create beautiful, organized patterns on cosmic scales. These spiral structures demonstrate that the universe routinely creates and maintains complex geometries through processes that operate according to elegant mathematical principles, governing density waves and gravitational dynamics. Our exploration of the galactic center's supermassive black hole revealed how extreme objects influence galactic structure while providing natural laboratories for testing fundamental physics under conditions impossible to recreate in terrestrial experiments. Sagittarius A** serves as both gravitational anchor and cosmic engine that helps organize galactic dynamics across enormous scales. The approaching collision with Andromeda demonstrates that galactic rotation patterns represent temporary configurations in cosmic evolution. This future merger reminds us that the universe operates on timescales that dwarf human experience while continuously transforming cosmic structures through gravitational processes that create new galactic systems with completely different rotation characteristics. Understanding our cosmic perspective revealed that galactic rotation is just one component in a vast hierarchy of motions that carries us through space at combined velocities exceeding 2 million miles per hour. This cosmic motion connects local galactic dynamics to universal processes spanning scales from individual galaxies to the largest structures in the observable universe. The formation story of our galaxy showed how 13.6 billion years of cosmic evolution transformed simple initial conditions into the complex rotating system we observe today. This extended formation process demonstrates how fundamental physics creates organized structures through processes operating over cosmic timescales, while highlighting the remarkable achievement represented by stable galactic rotation. The universal context of galactic rotation revealed that our galaxy participates in cosmic processes that operate throughout the observable universe, creating billions of similar rotating systems while maintaining unique characteristics that reflect specific formation histories and environmental conditions. As you consider the implications of traveling through space at 515,000 miles per hour simply by existing on Earth, remember that this motion connects you to cosmic processes that span the entire observable universe. Every atom in your body has participated in this galactic rotation for billions of years, traveling distances measured in millions of light years while remaining gravitationally bound to our cosmic home. The precision required to maintain galactic rotation over billions of years reveals the universe as a place where mathematical elegance governs physical processes on scales from subatomic particles to cosmic superclusters. The same gravitational principles that keep planets in orbit around stars also maintain the organized motion of hundreds of billions of stellar systems within our galactic disk. Understanding galactic rotation provides perspective on humanity's place in cosmic evolution while revealing how local, Processes connect to universal principles that operate throughout space and time. Our solar system's participation in this cosmic motion makes us active participants in one of the universe's most fundamental dynamical processes. The ongoing mysteries surrounding dark matter and galactic dynamics remind us that scientific discovery continues to reveal new aspects of cosmic reality. Future observations and theoretical developments will undoubtedly deepen our understanding of galactic rotation, while potentially revealing entirely new physics governing cosmic structure formation. The technological achievements required to measure and understand galactic rotation demonstrate how human curiosity and ingenuity can reveal cosmic truths that seemed completely inaccessible just decades ago. These accomplishments inspire confidence that continued scientific exploration will unlock even deeper mysteries about our cosmic environment. Looking toward the future, our understanding of galactic rotation will continue to evolve as new observational capabilities reveal additional complexities in galactic dynamics, while theoretical advances provide deeper insights into how gravity, dark matter, and cosmic evolution create the rotating systems we observe throughout the universe. The beauty of galactic rotation lies not just in its enormous scale and complexity, but in how it demonstrates the universe's capacity to create stable, organized systems through the application of fundamental physical laws. This cosmic elegance reveals deeper truths about how nature operates on scales that challenge human comprehension, while maintaining mathematical precision and long-term stability. If you found the cosmic mechanics of galactic rotation as fascinating as I hoped you would, subscribe and give this video a thumbs up. For more explorations of how our cosmic environment affects life on Earth, check out my video on how our solar system's galactic orbit influences ice ages. You'll discover how our 225 million year journey around the galaxy may affect climate patterns over geological timescales. Right now, as you finish learning about our galaxy's incredible rotation, remember that you are traveling through space at 515,000 miles per hour as a passenger on the cosmic carousel that is the Milky Way, participating in gravitational dynamics that connect you to the largest structures in the universe while carrying you on a journey through space and time that began billions of years ago and will continue for billions of years to come. A permanent reminder that we live in a dynamic universe where everything, from the smallest particles to the largest galaxies, participates in the eternal cosmic dance of matter and energy moving through the infinite ocean of space-time.